Okay, hello everyone. Hola. Welcome to my talk. I'm calling it Just-in-Time Architecture. This is a talk that I originally prepared and delivered internally at a previous employer, which is an online social games company. And during my time there, the company grew from being sort of a scrappy, small startup to quite possibly Australia's fastest growing and easily most profitable scale-up, from around about 100 employees to now approaching 2,000. And I think this story makes me fortunate. Stories like this are uncommon. At any given time, there are probably only roughly 1% of organizations that are actually going through this stage in their journey. And many startups will actually fail at this exact point. So that means now I get to talk to you all about this experience and reflect on all the lessons that we learned as we went through that. This is actually really exciting. I've got people standing at the back. We've got a full house here, so that's cool. So a bit about myself. My name is Macklin Hartley. I'm from Perth, Australia. I guess 3 facts. I'm really enjoying my time here in Porto. It's a great city. I've had about 3 billion pastel de nata since I've been here. And I'm actually soaked from about here downwards because I got caught in the rain here this morning. So I'm hiding behind this podium so you can't see that. So we'll start with a software development journey. With a company, I'm going to talk sort of hypothetically, so I'll be talking about an online gaming company who shall remain nameless at this point. So let's imagine we all work for an online gaming company, and our product managers and stakeholders, they believe that we can make more revenue by allowing our customers to personalize their experience in-game. So the stakeholders call a meeting with the team, they get all of the engineers and the testers and the designers together, and a meeting like this might sound a little bit familiar to you. Lots of ideas and brainstorming happens, and there's lots of debate about how best to approach this problem. After the dust settles, the product manager grabs a marker, walks up to the board, and draws out some squares that look a little bit like this. I realize that this is a bit of a higher fidelity than a sketch, but you'll just have to imagine. So what we have here is we have an online avatar store where players can choose to buy which avatar they want to buy. We can see that we have our balance shown up the top, and a preview of each avatar is shown with the name, the cost, and a buy button beneath it. The avatars also have an artificial scarcity, so once they run out, they're gone. So that's a bit like an NFT, although we don't really talk about those anymore, right? Over in the corner of the room, we can see that the front-end engineers and the UX team, they both light up immediately. You can tell that they've both just come up with the ideal front-end architecture, and they're keen to start, so they leave the room. Now, the back-end engineers need to decide on what the server-side application architecture is going to be. So I'll say at this point, I'm going to be talking about server-side application architecture at this point. I'm leaving out front-end. That can be a different talk. I'm sure there's many people you can watch here at this conference talk about front-end architecture as well. So the team, they start to think about all of the steps that are involved in the workflow. Firstly, they figure out that they'll need to have a step in the workflow to first validate the request, because we don't want people cheating the system. The server side will need to ensure that the customer, for example, is valid and that they have sufficient balance in order to purchase this item. Then the server will need to be able to deduct that balance and that cost from the customer's balance, and then once that balance is deducted, the avatar can be assigned to that player in their inventory. You'll start to notice some recurring language, some ubiquitous language here. So I've underlined that. We've got the words checkout, deduct, balance, assign, and inventory. So we'll come back to those. Knowing that this is a reasonably common and simple workflow, the team decides that the easiest way to approach this would be to use a monolithic architecture. How this works is there's a single server and its database, and they talk to each other. And this is categorized by handling multiple operations in a single request lifecycle. There's no need to communicate with any other systems. It's just a server and a database paired with each other. And this means we can leverage a really powerful thing called atomic database transactions. So if we zoom into that a little bit with the atomic database transaction, let's ask ourselves, what does that mean? They allow us to perform a series of operations on the database such that either all of those operations succeed or all of those operations fail. And this prevents us from entering any weird invalid states, for example, where we debit the balance but then don't assign the avatar. This eliminates most of the complexity of managing that state. And this is a feature of most, if not all, major database technologies. Almost all of them can do transactions. And this is called a monolithic architecture. How do I know what is a monolith? How do I know one when I see it? We might all have the same idea, but let's define it. For me, I associate it with old software. So Microsoft Word, Adobe Photoshop, software that's been around for a very long time. Maybe your favorite video games as well. That kind of software used to come in a CD, in a box, right? Just because we built an application recently using a modern language or framework doesn't mean it's not a monolith. Monolithic architecture is usually hosted within one code base that couples all of the business concerns together. And to make a change to this sort of application requires deploying the entire stack at once. This can sometimes, but not always, make updating the stack restrictive and time-consuming, leading to making updates infrequent and costly relative to the package size. So let's fast forward a year. The product is successful, and the team has grown in size. The monolithic architecture has been really productive for the team up until this point. We've added a few more team members to the team and a lot of new features. Some problems are starting to show up though. The new engineers on the team are complaining that, for example, the IDE takes a long time to load. The build time has increased, and it takes a long time to run all of the tests too. Regular merge conflicts happen because everyone is working on top of each other on the same code. The boundaries are not isolated, and there's no separation of concerns. There's a high batch size for small changes, so if we change one thing for a small feature, a bunch of other things need to change at the same time, otherwise things break. And that's really frustrating too. New features in our app are also not individually deployable. So it's not a problem from a downtime perspective. The team did the right thing early on and set up zero downtime deployments, but they take 20 minutes. And if we want to be doing more than 20 deployments a day, we've got a large team, that means they're now back to back. We have used all of that time. So again, some of the new engineers also have heaps of experience using Kotlin, and the whole team is excited to start using it. But up until now, everything's been written in Golang. So we'd have to do a huge project to migrate everything over, so we can't really do that either. So I'll come back to all of that in a minute, but to summarize, this solution was really fantastic. It did what we really needed it to do at the time. We validated the hypothesis about personalized avatars, and the product became really successful. The chosen architecture also has some unique and powerful characteristics. We can, for example, do atomic database transactions. While that sounds really good, this is not a perfect system. There are downsides. Monolithic architectures have a coordination overhead that is amplified by the team size. They do little to enforce modularity, and it becomes easy to create the infamous big ball of mud. So a bit of a detour. Hands up, who here bought a coffee this morning? Like actually paid for a coffee at the shop? Yeah, there's one person, cool. The flow I described is like going to a cafe to order a coffee. From the customer's perspective, the customer gives the cashier some money. The cashier checks that it's enough and validates it and puts it into the till, and then the team will go make a coffee for you. There isn't anything special happening here. It's actually a pretty typical commerce workflow, and it's seen everywhere, in real life and online. It's probably a good time for me to do a little side note about how coffee is consumed in Australia, because I've originally given this talk to Australians. So some of this might not make sense if you're from Portugal or for other parts of Europe. The most popular coffee drink in Australia is a flat white, so that would be something like a latte or a mia de leche here. Hopefully I get the pronunciation right. I would say that in Australia, because a flat white is the most common drink, or latte type drink is the most common drink, a latte art's a really big deal. So it's more a part of the sit-down coffee experience. Whereas it's quite common, I think, here to drink coffee without milk, I've noticed. So if the way I'm talking about coffee seems a little strange, that's why. So monolithic architecture is a bit like a tiny cafe operated by a single person. This is Adam, he owns the cafe, and he currently has 3 responsibilities. He has to take the orders, make the coffee, and then pour the milk. He works quickly, so he's never had any problems or issues keeping up with demand for the customers. Plus, his cafe is quite small, so he doesn't have heaps of customers. But the problem is he's not very good at making latte art. Look at that, that's terrible form. That's just awful. Yeah, that's what it's meant to look like. Adam feels he's actually better at talking to customers and taking orders. He remembers everyone's name, and he's never really been very good at making the actual coffee. I want to reiterate that the problem here that Adam has isn't one of scale. He can make the coffee fast enough and serve it to his customers, but he wants to give the customers the best possible cafe experience, including having the best coffee in town with the best latte art. So what is he going to do? Adam hires 2 employees. So he hires Sarah and James. Sarah is an expert in pulling coffee, so she is responsible for operating the coffee machine. And James has a master's degree in latte art from Melbourne University, so he's responsible for pouring the milk. That's a joke, by the way, we don't have university degrees for making coffee. This is now 2 less things that Adam has to worry about. He can focus on providing really good customer service. He can be talking to customers, remembering their names. And importantly, everyone in this workflow here can work separately and independently of each other. And I think this makes sense in a cafe. We see this all the time. Can we do something similar in software? Hands up if anyone can see where this is going. Right? Yeah, this is a microservices cafe. So the engineering team has just heard a lot about this new architecture called microservices, and they decide to do some research. They find out that a microservices architecture is a way that we can help enforce boundaries, which is one of the problems that we have at the moment. This also allows parts of the system to be deployed independently of others. It also enables polyglot development, meaning the engineering team with the new engineers can start using Kotlin without needing to do a huge rewrite. So that sounds like it can solve some of our current problems, I think. So the team has agreed to split up the monolith and create boundaries between each domain concept. Now we have the store, and that tells us what things are for sale, balance, which is how many coins I have, and inventory, which is all of the things that I own. And these names are based on some of that language that the team identified earlier, that ubiquitous language. So you remember the slide, it said store, balance, and inventory. And this is what the workflow now looks like. We still have a workflow with a single request lifecycle. We can see here that the client sends a checkout request to the store, and the store receives information about the customer and package from its database to validate the request. The store then sends a request to the balance service to deduct the balance. The balance service goes and deducts the balance and saves that information in its own separate database. Then sends a response back to the store service. The store service can then send a request to the inventory service to assign the avatar to the customer. The inventory service then adds the item and saves its information into another separate database before responding to the store service. Then the checkout workflow is now done. The store service can return a response to the client saying that the checkout is completed. The team's pretty happy with themselves. We did it, team. We did microservices. This was easy. I don't know what everyone was talking about. But hold on a minute. After deploying our new microservices, everything starts going wrong. Our customers are unhappy. They're reporting that their balance is deducted, but they don't get the avatar. Customer support was receiving thousands of complaints from customers every day, and engineers have to start wasting a lot of time helping customer support by manually compensating those customers who didn't get their item. And then perhaps worst of all, fed up customers are just leaving and revenue's dropping. So the team decided to look at the architecture a little bit deeper and investigate possible failure scenarios. The team notices that occasionally the balance service fails to return a response after deducting the balance. The store doesn't know whether the balance was deducted or not. It never gets an answer. It can't proceed to the next step of the workflow to send a request to the inventory to assign the avatar. In this scenario, the workflow timed out and we were left in an incomplete state. The customer's balance was debited, but the item doesn't get assigned to the inventory. This is one of the 8 fallacies of distributed computing. This is impacted by one of the 8 fallacies of the distributed computing called the network is reliable. Because we've introduced more network calls into our workflow, there are now more failure points. How can we know without the response from the server how to proceed with this workflow? In our previous workflow, we relied here on atomic transactions to prevent our application from even entering into this state. So typically with a distributed architecture like this, there's not really a way to reliably replicate atomic transactions. We don't have the luxury of opening up a transaction scope, completing our unit of work, and then committing that transaction once we've finished, or rolling it back if it failed. Each of these services, the store, the balance, and the inventory, are running on different databases. They could be even different database technologies. One could be Postgres and the other one could be MongoDB. There's this one idea called a two-phase commit, which aims to replicate atomic transactions. It works, unsurprisingly, in two phases. We ask each service to prepare itself to be ready to do the transaction. And if all services are ready, we ask each service to then perform the action, otherwise they all roll back. This usually involves taking a lock on any of the resources that are required, and total transaction time is proportional to the time taken by the slowest server. The team is concerned about adopting this pattern because it will cap write throughput in the future as we continue to scale. So for that reason, two-phase commit is not really a commonly used pattern, and mainly for that reason. It's essentially a blocking protocol. The coordinator, in this case the store service, has to wait until all participants complete and is therefore coupled to the performance of the slowest participant. You can also run into tricky situations where if the coordinator fails during the transaction, a bunch of services could be left with locks hanging open and not really knowing what to do. They have to rely on either the coordinator coming back online or on timeouts. One of the engineers suggests that if the first request fails, we should just retry it and ask the service to deduct the balance again. However, because we're now using microservices, the balance service doesn't really have its own context of the given request, and whether the request is a retry or if it's another request with the same parameters. So here is where we need to introduce a new concept called idempotency. Idempotency will allow the balance service to know whether it has received and processed a given request already. To make our retried request idempotent, we have added a request ID property. If the request ID matches a request that we have already seen and already processed, then the balance service skips processing and the request returns immediately. If a given request has a unique request ID that has not been processed already, we can see here that the balance service knows to process it as a new request rather than a retry of an existing request, even if all of the other parameters match. So now that our requests are idempotent, we can add retry logic to our workflow. So this is what our workflow looks like now with retry logic. Now, when the balance service occasionally fails, our store service can simply retry the request with the same request ID until it gets a response from the balance service without it timing out. Once the retry logic concludes, the rest of the workflow continues on as normal. However, now, whenever the balance service occasionally fails, things start to get much worse. The team observes more and more requests are piling up and retrying over and over. When the balance service comes back online and finally recovers, it gets this huge flood of retrying requests that are sent at the same time from all of the hanging services. The balance service never really recovers because there are too many requests backed up. Since we're not closing our request life cycles until this workflow is complete, lots of requests to the store stay open and start putting requests on that service as well. This effect is known as a retry storm. Generally, what we've learned here is this kind of workflow is unreliable. There are many examples where the failure of one service leads to the failure of the entire workflow. And the name for this is called availability coupling. This workflow needs all three services to be available at the same time. If each service has a 99% availability, then the availability of the workflow as a whole is a multiplication of those three availabilities, which turns out to be 97%. It actually gets worse. 97% is probably very good if you're in university. That's like a high distinction. But in our case, that means our system can be down for it can be unavailable for as many as 11 whole days per year. So imagine if Netflix was just down for 11 whole days per year. It's not really acceptable. And it gets worse, again, as I said, when more services are added to the workflow. So if you recall, there's now 3 employees in our cafe. We have Adam, who talks to the customer and takes payment. Then we have Sarah, who pulls the coffee shot, and James, who handles the milk. Let's say Adam takes payment from the customer. Adam then orders Sarah to pull the coffee shot. However, at this time, Sarah's just had to duck out to an emergency call, and she's left her station. Sarah's not there. What does Adam do? Well, in this case, Adam just drops the order and moves on to the next customer. This resulted in the payment being taken, but the coffee not being made for the customer. And here, in this coffee shop as well, there's also availability coupling. Although Adam and Sarah are working on different things and able to work independently of each other, Adam needs Sarah to be there when an order comes through. Otherwise, the order is lost. I will say probably that cafes don't normally work like this. They've got solutions to it. We'll get to that point. But yeah, here we have availability coupling as well. So to recap, by splitting our monolith into multiple services, we're able to enforce boundaries and allow the team to work independently and deploy services separately. But other different problems arose when the team moved to multiple services. Availability of the system as a whole decreased due to availability coupling requiring all 3 of those services to be available at the same time. Balances were deducted, but avatars weren't being assigned to the customer's inventory, and we had incomplete workflows. What we'd implemented was not microservices, but probably instead of known as a distributed monolith. Cool, so we have to go back to the drawing board now. We've got to figure out another way to do this. Firstly, let's talk about event-driven architectures. Firstly, let's cover exactly what an event-driven architecture is, starting with an event. So what is an event? An event represents a change in state, a representation of something that has happened. It's an immutable fact, so generally events don't change. We can't rewrite history. And usually you have to assume that there's something that's happened in the past. So assume when you're seeing an event that it's something that happened potentially a long time ago. We don't know. AWS defined an event-driven architecture as an architecture that uses events to trigger and communicate between decoupled services. And it's a really common architecture pattern that's applied to microservices. So I think this could be a way to solve some of our problems. The team starts doing some research about event-driven architectures, and when they start digging into it, they notice a few patterns keep emerging. They've got this thing called event notification and event carried state transfer as different ways of producing events. So let's explore what those 2 things mean. Let's start with event notification. What happens is we send an event of something that happened. Essentially, all it gives us is the identifier for the thing that changed. And we can see we created a checkout, but just the identifier is there. This allows the consumer to decide whether or not it needs to do anything with that information. If the balance service gets this event, it would need to deduct the customer's balance. But which customer and by how much? In this case, the balance service must query the store about the checkout details, and the source of truth remains the store database. It knows everything. So back in our cafe, event notification, this is what event notification looks like in the context of a cafe. Adam is at the counter and he takes an order, and then he shouts over to Sarah, "Take away coffee." And Sarah's like, okay, not enough information. She has to go and ask Adam for more information. "Hey Adam, what kind of coffee is it?" It's a flat white or a meia de leche." "Great, is it small or large?" "Oh, it's large." So Sarah gets a little bit frustrated because she has to ask Adam over and over again for more information. So while this isn't ideal in the context of a cafe, it's not all bad news. It's actually a totally common and acceptable way of applying an event-driven architecture, particularly on a legacy system that doesn't initially support it. With event notification, when an event is raised, we ask the source of that event for its view of the world. Event notification is nice because the source of the event is always the source of truth. But the downside here is that additional request for information to get it. If there are many things that are interested in a particular event, they'll all ask for information at the same time. So this can be pretty chatty. There's got lots of requests for extra information. So what if we add some additional state to the event? So this is the same event as before, but all we've done is we've added some extra information onto it about the event so that we don't have to get that information later. And this is called event carried state transfer. This avoids the need for the balance service to query the information from the store because it's in the event. We don't need to make another request to get more information. And that's great. But potentially, now as soon as we have this information, it's potentially stale. It's no longer true. If we read it again later from our database, the new information we might have might not match what's on that event. The database in the store might have new events, new information that we've not yet received, and that's known as eventual consistency. So back to the cafe again. Adam listens to Sarah's frustrations, and he went and bought a receipt printer. Now when he takes orders, he prints out a ticket, and he places that ticket on the little thing on the coffee machine, and Sarah can see all the information that she needs. So it says, a large takeaway with all of the information, a mia de leche. And this works out pretty well most of the time, except occasionally, maybe a customer comes quickly up to the counter and they said, oh, they've changed their mind. Oops, can you please make sure that's decaffeinated? Now the information on that ticket is no longer relevant. If we don't change that ticket, Sarah might make the wrong drink. We should produce new information and a new event to say that that order is changed. This mostly works better in the context of the cafe, but it still has trade-offs. So we're not making all of those extra requests just to get more information. It's less chatty, but now we have potentially stale events and stale data shared across multiple places. The assumption is that any of these events are essentially stale immediately. They might not actually be stale, but we don't know unless we check. So now we know about the two different event-driven patterns. Let's talk about where events actually come from. How do we produce them? So events are usually produced as a side effect to a change that has occurred in the system. So here is an example where we inserted a checkout into our database. A checkout created event is created at the same time. We can send an event to this message broker for other systems to consume. However, the database and the message broker are two different systems. What if the message broker is unavailable at that time? This could lead to our event getting lost. We need to guarantee that an event gets published when the change occurs in the database. And we don't have the luxury, again, of atomic transactions here because these are two different systems. It's the same problem with our microservices. And I don't think we really want to figure out a two-phase commit here either. Unsurprisingly, there are a number of ways to fix this problem as well, each with their own trade-offs. There's 3 ways to guarantee that events are produced. We get transaction logs, the transactional outbox pattern, and event sourcing. So transaction logs are a feature that's actually offered by most databases. Transaction logs are created whenever inserts, updates, or deletes are performed on a database. You might have heard of something like this before, but by a different name. Maybe you've heard of change data capture. An event publisher can poll these logs and then translate those into events about the system before sending those off to a message broker. Probably the biggest upside to using transaction logs for event creation is that it can be enabled with minimal effort on legacy databases with no existing event generation capacity. You don't need to write any new application code to start streaming and capturing events from transaction logs. Just enable the transaction logging feature, if it's not already enabled, and start polling the log output. The downside here is it's using the low-level database logs instead of business events, so you create a coupling to the schema of those logs. Alternatively, we can use the transactional outbox pattern instead of using transaction logs. How this works is we save the business event into a separate table called the outbox table, and this, thankfully, can be done in an atomic transaction. This ensures that both the row in the table gets updated and the event gets inserted at the same time. And if either one of those fails, then they both fail. After that, a process could do what's called a destructive read for events from the outbox table. That means it reads them, and if it successfully processes them in an atomic transaction, it can then delete that row as well. That ensures that the data is read and processed before it is deleted. Once events are generated, they can be then sent downstream to the message broker. However, this step is not atomic. So you might, one of the problems here is you might get duplicate messages being published to that message broker if it fails. So again, this is a good choice for supporting an existing database that doesn't have any event generation capacity. It also allows us to avoid any direct coupling to those database logs, those transaction logs. There is, however, a downside in that this pattern requires an additional atomic insert on the database at the point of insert or update. This carries with it the potential maintenance and performance penalty. So as a third option, instead of saving events as a side effect, what if we could just make the events the single source of truth? We can do this when the data in an append-only event stream represents the superset of the equivalent data in a mutable table, and this is known as event sourcing. So downstream services can just poll the event store directly without needing to go through a message broker, although we can add a message broker if we want. Now we replace all of those existing tables, and if we ever want to bring them back, if we ever want to bring back the data in the same shape it was before, we would use what's called either a projection or a read model. One of the properties I personally really like about event sourcing is the use of the append-only model. So generally speaking, a stream of events in an event source system will have the event carried state equivalent of the comparable CRUD model. However, in an event source system, it also contains the history of all the changes, making it a superset of the current state. For example, the CRUD model on the left only stores the most recent value of the balance. So every time it changes, we're overriding that data and we're losing the previous value. Whereas with event sourcing, you can see on the right that we've got every single version of that amount that it's ever been. We're not losing any data. So event sourcing provides a complete, immutable log of every state change, which can make troubleshooting a lot easier. Event sourcing also has an audit log built in as an added benefit. It enables resilient applications. It enables us to reprocess data if we need to. It is, however, not generally as compatible with an existing system and existing database, like the transaction log or transactional outbox patterns. I tend to find that moving from a non-event source system to an event source one will typically require a rewrite from scratch and a really complex migration. So therefore it is an easier choice to make if you're starting from scratch. So to wrap it all up, we're going to talk about communication patterns. This is putting all of the pieces together. This is talking about how microservices can communicate with each other through event-driven systems. So one of the attributes of an event-driven architecture that I've not touched on yet is their reactivity. What that means is they're able to react and process information as it arrives, rather than later in bulk when it is retrieved, or at request time. But how are we able to do that? When building event-driven systems, we not only have to consider how events are produced, we also have to consider the patterns by which events are consumed. At a broader scale, how our services interact with each other in a distributed system. There are two common event-driven communication patterns that I'm going to talk about. The first one is choreography. Think of choreography as a bunch of services or participants performing in a dance routine. In a dance routine, if you didn't know, the way they work is everyone just looks to their left for cues. Each step is just handed off to the next participant in a choreography workflow. And then you have the other workflow, which is an orchestration. And that's like an orchestra. So with an orchestra, you have a conductor who's telling everyone the timing on which to play by. But the thing about a conductor is they don't play an instrument themselves. But on the flip side, the orchestra doesn't play without the conductor. That's not possible. So our flow as a choreography workflow might look a little bit like this. The workflow sequence is distributed to each of the participants. The participants communicate with each other through events. So we can see here the store receives requests to start a checkout from the client. When this happens, it raises an event saying the checkout was created. So that's up there. The balance service is waiting for checkout created events. When it gets one, it knows its job is to deduct the balance. So it deducts the balance and produces a balance deducted event. The inventory is waiting for balance deducted events. When it gets one, it can raise an avatar assigned event. And then if we go back to the store, we can see that it's waiting for that avatar assigned event. And when it gets one, it knows that it's time to inform the client that the checkout is complete. So choreography is probably a lot like how a cafe works naturally. We have Adam who takes the order, and Adam passes that order on to Sarah, and it's now Sarah's responsibility. Sarah then pulls the coffee. When she's done, she can pass the coffee over to James, and then James frosts the milk and pours it. And then James, once he's done, calls out the customer's name and the order is complete. One problem is when a customer wants to know where their order is, let's say it's taking a long time. Who can answer that question? Well, the problem is it really depends on where the order is up to in the system. If we ask Adam, all he knows is he took the order, took the money, and passed it on to Sarah. He doesn't know where it is now. If we ask Sarah, she says that she's pulled the coffee already, and she's done, and she's not responsible for it anymore. She's passed it on to James. And if we look over at James, he looks a bit flustered. He's got a big queue of coffees that he has to add milk to. So we should probably just leave him alone, but he probably has your coffee. So with choreography, the problem is we may have to ask each participant in order to understand where we are up to in the workflow. To recap about choreography, I think of it as elegant. It's quite simple in the sense that a dance routine is quite simple as well. Each person only has to look to their left for cues. Each participant only consumes the events that they care about, and once they complete their job, they raise more events that become cues for the next participant. The problem here is that it's costly to observe. So if I want to know where the workflow is up to, I probably need to talk to every participant. There's no central place that I can look to for progress. The decentralized nature of choreography also ensures that it gets very complex when the size and the number of steps in a workflow increases. Particularly when you have things like nonlinear workflows with multiple branches or complicated error handling requirements. They become more difficult without centralized management. I'm just going to stop and have a drink. Okay, so before I talk about orchestration, let's talk about the difference between events and I'm going to introduce a new concept called commands. So you can see here our events are orange. Services can listen to these events and that are produced by each workflow that they care about. As we can see here, the balance service is listening to checkout created, but then also game registered, daily reward claim, achievement completed. For every new workflow, it needs to subscribe to more and more events and know more and more about how the world is, more and more about the world around it. Like a lot of things in software, I think we could probably make this a little bit simpler if we just flip it around. So with commands, the service doesn't need to know about all of these other workflows. Instead, the balance service just does two things, and it exposes two commands. It handles the add balance command and the deduct balance command, and it does nothing else. We know that from the definition a few slides back, the balance added is past tense. So that sort of is a marker for an event. Whereas commands, because they indicate intent, it's an instruction to add the balance, then generally you'll see them written in a future tense. Commands and events sit on the either side of the thing that happens in a workflow. So you have add balance, then you're adding the balance, and then you've added the balance. So now let's look at our workflow using orchestration. So we can see here we're using commands instead of events to coordinate this workflow. With orchestration, the workflow starts off the same. A checkout created event is created by the store. The event is received by a new component called the checkout process manager, which now manages the workflow from this point onwards. It begins by sending a deduct balance command to the balance service. The balance deducted event then gets triggered, and we move on to the next step of the workflow, which is to send the fund checkout command to the store to notify that the checkout is being funded. The checkout funded event comes back and then triggers the next step in the workflow, which is to send the assign avatar command to the inventory service. The avatar assigned event is produced and then triggers the next step in the workflow, which is to tell the store that the checkout has been completed. This workflow is centralized and is managed by that single process manager in the middle. Workflow participants do not need to subscribe to events, they only expose commands. The balance service exposes the deduct balance command, for example, and the inventory exposes the assign avatar command. The workflow steps here are still triggered by events. So for example, the checkout created event triggers the first step of the workflow, and the balance deducted event then triggers the next step of the workflow, and so forth. With orchestration, we can also handle unsuccessful workflows. So if we have unsuccessful workflows due to business constraints, say for example, we have a customer who already has the avatar, and we have a business rule that says you can only buy one of each. So let's imagine they've already bought this avatar. Before we end up in the state where they've got two avatars, and that's an invalid state, we need to what we can do instead is if we receive sort of an error from that inventory saying that we've done that, we need to basically reverse all of the transactions that we've done before. Where am I up to? Yep. So we can see here a reverse operation, which is an add balance command, which is basically the opposite of that original deduct balance command, is sent, and then that needs to be handled. After the assignment fails, the checkout failed event is then also raised. That event triggers the process manager to refund the checkout at the end. So upon success, I'm now lost. Cool. So basically this workflow here and the act of adding the balance back is what's known as a compensating transaction. A compensating transaction is similar to, but different to an atomic transaction. It's a separate transaction that's performed out of band, unlike an atomic transaction, but it's the same in the sense that it's used to roll back to the original state. So the cafe is growing and now also sells food. Adam decides that it's time to take on more of a management role to make sure he's managing staff and orders. A customer orders a coffee and some food, so Adam takes the order. Adam now makes sure that orders are handled properly, so his first job is to pass the order on to Sarah. Sarah starts pulling the coffee shot, but then at the same time, Adam can walk over to the kitchen and ask the kitchen staff to make the food order as well. After Sarah is done pulling the coffee shot, Adam then makes sure to check in with James, who is handling the milk. If a customer needs to know the status of the order, they can now ask Adam, because he's centrally managing that workflow. Although this centralization now means the manager is now a single critical point of failure. So Adam can't really take a break now without handing off this role to someone else. He also finds that sometimes he gets a little bit overloaded when it's really, really busy because he's a single central point of failure at the moment. So to recap about orchestration, with orchestration the workflow logic is centralized. Events are still used to proceed through the workflow, but commands are also used by the orchestrator to communicate with those services. If someone wanted to figure out the current state of the workflow, they can go to the orchestrator and ask. This, however, also means the workflow has a single source of failure. So if the orchestrator ever fails, then the whole workflow stops. Something else to consider is how to scale a workflow with a single orchestrator. How do we enable this workflow to have multiple orchestrators so that they don't become a bottleneck? Is it even possible to do that? Maybe we can't scale the orchestrators horizontally, but we have to look at ways to enable them to process faster. So we could do batch processing, for example. Not something we have to do as a consideration for our own problems, but also not generally a problem with choreography as a communication pattern, just to know. So yeah, just to recap all of that, we went on a bit of a software development journey. So we started by building out our avatar purchase workflow. We went from a monolith, which worked well in the beginning for us, and we moved to a microservices architecture. We introduced all sorts of problems that were really unexpected, because really what we built was a distributed monolith with availability coupling. We sought out ways to improve this with an event-driven architecture. So I told you about two different types of events, which is event notification and event carried state transfer, and then three ways of producing those events. So you have transaction logs, the transactional outbox pattern, and event sourcing. And then to stitch it all together, we talked about communication patterns. So I talked about choreography and orchestration. Both patterns use events to trigger the next step in the workflow. Choreography uses events to communicate between services directly. So it's elegant, decentralized, but difficult to observe. Whereas orchestration centralizes the workflow. It uses commands for communication, but introduces a single point of failure. And this is the end of the journey. I guess the key takeaway of this is this journey was about using the architecture that was suitable for the problem that we were facing at the time. Each of these architectures served its purpose at the time that they were needed. We started by integrating into an existing monolithic architecture that was already working well for the small team. The team got to market quicker and saw success early, and the product was successful. But eventually the team grew, and then the team outgrew the architecture and decided to transition later to microservices. This architecture allowed multiple teams to deploy independently of each other. But there was more planning and work required in order to build a reliable system, and they had to navigate a few bumps along the way. It was better to make those, to run into those bumps later in their journey, once the team was more established. The decisions and trade-offs that were made at each stage of the journey were appropriate to the problem at hand. And I guess the key takeaway here is there's no one-size-all-fits architecture. Each stage in that journey required a different architecture that evolved with the product. So if there's no one-size-fits-all architecture, I think our jobs as architects is to find the best architecture to suit the problem at hand. How do we do that? There's two phrases that I think you'll hear most software architects using and saying on a regular basis. The first one is "it depends," which is relevant here, but probably maybe not that useful. Maybe another more pertinent phrase in this case is, what problem are we trying to solve? So we start with the question, what problem are we trying to solve? Are we a small, maybe 5-person team trying to find product market fit? Do we really want to be spending the majority of our time searching for product market fit, trying to make a product that's successful? Or do we want to spend most of our time building a globally distributed, fault-tolerant microservices architecture with 0 users? Had our team chosen this microservices architecture too early, the team could have run into those availability couplings problems really early on and perhaps never succeeded. So at early stages, our team's goals should align more towards meeting our customers' needs in the near term and as cheaply as possible. And that's it. Thank you. I'm going to supplement it a little bit with, if you get a hold of my slides, I've got some other talks here that are fantastic to watch over as well. I tend to find watching talks by other people is the best way to learn, so this one's particularly good. You want to take your pictures of it. This guy actually spoke after me when I presented this one at Yao, and they complemented each other really well, so if you want to see this one, it's a good one to watch. This one goes over the event patterns that I talked about before. Martin Fowler's fantastic. He's a fantastic orator, so he speaks very well. He's very clear. And this one's a really good one to talk about communication patterns, choreography and orchestration. Lots of detail in here. He's an expert. Thanks, guys.